as little homework as possible. So 7-1, we're into our circles unit. Super huge unit. Once again, it'll really prepare you for your ACT. It really will. I'm not just saying that. Okay, so first of all, we need to go over some vocabulary. This should not be new to you. If it is, you're going to have to catch on quick. Okay? Because you did learn this last year, or you should have. Okay? So a minor arc. A minor arc is made from the central angle. So remember, central angle means starts at the center of the circle and works its way out. So looking at this one, you see how this is a central angle and works its way out. The minor arc is the arc that intersects the central angle. So do you see how arc AB is my minor arc? It's called a minor arc, okay? Then a major arc is the arc that eats, I just say eats, it entraps the minor arc. So do you see how this blue arc entraps the minor arc? Kind of eats the minor arc. Okay, so that would be called a major arc. So it entraps the minor arc. So arc A, C, B. Major arcs are always stated with at least 3 points, usually within 3. So we could have, like, if there was another point on here, such as point D, the same major arc could have been named ADB instead of ACB, because do you see how that still makes up the major arc, everybody? Okay.
So if there was like a C and D there, could that be a central angle too, just a bigger one?
So if there wasn't a C or D there would be no way of specifying, because if you say AB, that's technically the major arc as well. So there would be, if they were asking you minor arc, major arc, there would be another point so that they knew you knew. Good question. Okay, so some more vocabulary. Semicircles, guys. This is pretty obvious. We know that semicircles, halfway around a circle, the angles add up to be 180 degrees. We know that, right? So halfway around the circle adds up to be 180 degrees. Those are also called straight line angles. Okay, a full circle's angles add up to be 360 degrees. So this full circle, the angles inside add up to be 360 degrees. Now looking at this, in this example, there are multiple 180 degrees. We could go on forever. Doesn't that make up 180 degrees? Doesn't that make up 180 degrees? Like, we could do this all day long. Doesn't that add up to be 180? Yeah? You guys see what I'm saying? So we could do this all day long. There are just multiple 180 degrees in this example. And then all angles add up to be 360 degrees. Okay, central angles. So, and a central angle a central angle is equal to its intercepted arc. We know that, we did learn that a little bit ago. But you should have also learned it in secondary too. So a central angle, an angle that starts in the center of the circle and works its way out, that angle will equal its intersected arc. So do you see how this intersects this red arc? Angle 20 degrees. So what is the red line? What's the arc? If this is 20 degrees, what's the arc? 20 degrees, right? Everybody, are we good? Are you paying attention? Okay. Now remember that we could actually find that physical length, couldn't we? Didn't we just learn that a little while ago? What would we change it to? Radians instead of degrees, right, everybody? That's the physical length. Okay. This is something you should have learned last year. Vertical angles are equal. So vertical angles are angles that are straight across from each other, but they have to be made from the same 2 lines. So do you see how it starts at the center of the circle, and we have this line and this line? They both go through the center of the circle. Does everybody see that? So they make central angles. Sorry, not central angles. They do make central angles, but vertical angles. Do you see how those red lines are vertical? Straight across from each other, exactly opposite. They're made from the same lines. So those are equal angles. So if those angles are equal, then wouldn't their arcs be equal as well? Okay, so we're going to be doing some just kind of thinking through some circles today. All right. So let's look at this picture and let's answer these questions, and then I'm going to let you work, okay? So answer these with me and ask questions if you have them. So it says, what's arc ABC? So arc ABC, okay? Well, first of all, let's figure out all these angles. Why not? Because we're going to be finding lots of arcs. So if this is 30 degrees, and this is 20 degrees out here, if this is 20 degrees, wouldn't this be 20 degrees? Isn't it a central angle that's equal to its arc? So this is 20 degrees. Now, isn't this a straight line angle? Okay, so wouldn't that add up to be 180? So tell me, what's this angle right here? 180 minus 30 minus 20.
130. 30.
130, right? 180 minus 50, guys, okay? It's 130, okay? So we can go about this a couple different ways. Next thing, this is 30 degrees. So wouldn't this be a vertical angle to this? doesn't this line and this line cross to the center, making up 2 angles? So if this is 30 degrees, this vertical angle is also 30 degrees. Now you can continue to solve this many different ways. I would just go about it this way. Isn't this a straight line angle?
Yeah.
So that's 180 degrees, right?
150.
So 180 minus 30 is 150. Okay, so we've gone through and we've filled in all our angles here. So now we can enter the arcs. So these are all central angles, so we know central angles equal their intercepted arc. So it says, what's arc ABC? That would be right here.
Yeah.
What's arc ABC?
50.
50 degrees. Does everybody see why? Okay, 30 plus 20 is 50 degrees. Okay, what's arc DC? If that's 130, then its intercepted arc is 130. It's a central angle. Very good. Arc DEB. So looking here. DEB. 30 plus 50 plus 30, right, everybody?
210.
Sorry, did I say 50? 30 plus 1, 50 plus 30, right, everybody? 210. Good. So arc CBE. We start C, go to B, then T. So CBE. So that would be 200. Is everybody comfortable with that? Okay. Do 1 through 15 on the worksheet. So on the ECT test, if you're given a circle and you're ever asked to find like an arc, no, a central angle equals its intercepted arc. But a central angle only is a central angle if it starts from the very center and works its way out. Does everybody understand what I'm saying? So never assume if it doesn't start at the center and work its way out that its arc is equal to its angle. Okay, so now this is something you need to have memorized for your ACT exam. You need to know some formulas for finding areas and circumference and some volumes. So circumference of a circle is 2 pi r. Circumference of a circle is 2 pi r. 2 pi times the radius. Now, so given a circle, if it says find the circumference, it's pretty simple. So looking at this example right here, we're going to find the circumference, which, let's go ahead and do that. What's my radius? 10's in the middle, so we can assume that this radius would be 5. So then our circumference would be 2 pi times 5, right? So that's 10 pi, right? And if we wanted, we know that pi is just a number. If we wanted to get down to the nitty gritty, we would call that 31.4. Because I typed into my calculator 10 pi. Does that make sense? 10 times pi. So you'd write both. This answer is what you would most likely see on an ECT, and I like that answer better. But it doesn't hurt to write out both. Is everybody comfortable with that? Okay. Do 16 through 19. On number 19, draw out some circles. Don't just raise your hand and say, I can't do it. If you haven't tried and really thought through it, you can't ask me a question. So, I promise you can do 19 if you can find a circumference of a circle. Okay? So you do have the information. Draw yourself a picture. I had to draw myself some pictures. Okay, here we go. So remember that we did learn how to find the length of any arc. Any arc in general, as long as you know the radius, and as long as you know the distance of the angle, right? So we did learn this formula. So you can find the physical arc length if you use the formula. S is equal to R times theta. So the radius times theta. So S stands for, a lot of people said to me, what does S stand for? That means side, side, which means length of the arc. That's what we're looking for. You take your radius times theta. Now, if we're finding a physical length, can we use degrees? Don't we need to use radians?
Yep.
Okay, so when we need to change 30 degrees to radians. So you can do this a couple different ways. You can do that first, change 30 degrees to radians, so you multiply by pi over 180. Or you can just say, okay, this is how I'm going to do it. I'm going to do it all in one, because I don't want to have to do 2 steps here. So I'm saying if I'm asked what's the length of this arc, I say, okay, I know that it's radius times theta. So I say S, or question mark, because that's the arc length, is equal to radius, which is 5, times theta, which is 30 degrees. But I don't want that in degrees, so I should have multiplied that by pi over 180, right? So you can, isn't multiplication all the same? So wouldn't it be okay to just put it in right here? Multiply by pi over 180. If I convert it first and then put it in, won't it be the same thing as if I put it in right there? Okay, so that's just what I'm going to do. So then I'm going to calculate that in my calculator. 5 times 30. We don't type in pi because pi, then you can't change it back to a fraction. So type in your calculator. We multiply straight across. So 5 times 30 times pi. So what's on top?
Just 30.
We're simplifying this.
So
Guys?
it's 150 over 80.
Okay, so you got 150. You multiply those together and a pi on top, right? And on bottom we have 180. What does that simplify to be? 150 over 180. 5 pi 6. So 5 pi 6. That is the pretty answer, which if we wanted to know, once again, if we were an engineer, we'd be like, what do you mean 5 pi 6? I want the actual amount. So we'd say, okay, 5 times pi, 5 times pi divided by 6. Okay, you're going to be going 2.6 miles if you wanted to be an engineer and go technical. Does that make sense, everybody? Are you getting what I'm saying? I can't tell because you're all just like zombies, and it's driving me insane.
Yes.
Okay. Okay, so once again, let's do one more. Find, number 23. So it says find the length of the arc. So looking at this, we're like, okay, this is 120 degrees. Is that the central angle as well? Isn't this arc equal to the angle? So that's 120 degrees, so we're good. We know S is equal to radius times theta. So S is equal to our radius times theta, which is 120. But we need to change that to radians. So I'm just going to multiply by pi over 180 right here, right now. So then you'll take your calculator, type in, I'm just going to simplify it all in once on my calculator. 9 times 120 divided by 180. So you get 6. So that would be 6 pi. And if you're an engineer, that's 6 pi, which is 18.8 inches. No, we found this arc length right here. Because if this is 120, so is this, right? So that'd be finding that arc length.
Okay, so we're just putting the 120 against the physical length.
Sorry, what was the question?
We're just putting the 120 to the physical length. Like, so it's not.
No, it's just the reason this was actually written in their original. So then I put it in here so I can put it in my formula because it's theta, which is the angle. So.
But we're just, instead of like the length being 120 degrees, we're just finding that.
Yeah, because we want the actual length, not the. If we have it in degrees, that would just be all degrees. Yeah. Okay, do these problems. So you'll be able to go back. I just want to give you plenty of time to work on the last few that you're going to have to kind of use your brain a little bit more. So now we're putting it all together, okay? So the reason we went over all this stuff is for these, okay? They're not as hard as they look. So I'm going to do one with you and I'm going to let you go. You have to be able to think if you're in secondary 3. It's not just apply circumference. That's not how secondary 3 works. It's apply what you know based on those little facts that you do know. Okay, so number 20, it says the weeks. The wheels, what the heck was I doing? The wheels on Reggie's bike, hold on, that's gonna bug.
Reggie, holy cow.
Okay, the wheels on Reggie's bike each have a 20-inch diameter. His sister's mountain bike each has a 26-inch diameter. To the nearest inch, how much farther does Reggie's sister's bike travel in one revolution than Reggie's bike? So let's go through and kind of draw ourselves some pictures. It will be really helpful for this one. So first of all, the sister's bike Reggie's bike has 20-inch diameter, right? So here's a bike of a wheel of a bike, and that's 20. I'm struggling because I'm thinking and talking at the same time. Okay, so there's Reggie's bike. And then his sister's bike is a wee bit bigger, and it has a diameter of 26. Is everybody comfortable so far? So that's the sister. Okay, so now it says to the nearest inch, how much farther does Reggie's sister's bike travel in one revolution? Doesn't one revolution mean 360 degrees? Going all the way around the circle. Yeah? That is what it means. So physical length, wouldn't that be taking a wheel and going ding, 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 ding?
Yeah.
Okay, so wouldn't it be finding the full length around here? Yeah? So this is how I would do it. This is how I thought through it. First of all, we know that length of an arc is radius times theta, right?
Yep.
Let's find the length of each of these circles. All the way around the circle. So, S is equal to radius times theta. So S is equal to, what's my radius on Reggie's bike? 10. Now theta, how far around are we going? 360 degrees. So I'm going to multiply by 360 degrees, and then we need it in radians, right? Times by pi over 180. Okay, that's the length of all the way around Reggie's bike. Go, calculate it. 25?
Yeah.
Yep. So S is 20 pi. Now let's do this one. S is equal to our radius, which is... Guys, there's people like not even paying attention. So if you don't need me to do this one, I'll let you do it.
26.
So 13 times the theta, which is 360, and we're timesing by pi over 180. 26 pi. Okay, so how much further? Did you say 26 pi?
Yep.
Yeah, I got that same thing. Okay, so it says, how many, to the nearest inch, how much farther, because these are inches, right? 25 inches. So, you gotta be careful though, because that's pi inches.
6 pi inches.
No, okay, if we wrote 6 pi inches, we'd be on the right track. So let's actually find the actual inches on this one.
Oh. 18.8 inches.
Yep, so we will be doing 26 pi minus 20 pi, right? Which is 6 pi inches. So how many physical inches is that? Type it in. 18.8 inches. So do you see how you can think through that one? Yes? Okay. Sweet. That's the only one I'm going to do. So now, you're doing these ones. 21, 22, 35, 36. Go. Number 37 I'll do with you. So I'm doing it off the worksheet. So it says arc ST is 3 pi, arc ST, I must have wrote something wrong. Look at your number 37, I'm doing that. It says STO. The length of ST is 3 pi inches, and the measure of ST is 120 degrees. What is the radius of B? So I just left out my measure. Okay, so I drew a circle where, so it says ST, so we have an S and a T somewhere, is 3 pi. So isn't that going to be this length? 3 pi. And then it says that the measure of ST is 120 degrees, and it says what is the radius? So we say to ourselves, okay, don't we know S is equal to R theta? Yeah. S is equal to the radius times theta. So we know S, it's 3 pi, is equal to the radius times theta. Theta is 120 degrees. Which we need to actually, radius isn't in degrees, is it?
Nope.
So we need to change this to radians. So what is 120 degrees as radians? 2 pi thirds. Because radius is a physical length, not a degree. So we have 3 pi is equal to radius times 2 pi thirds. Because 120 degrees in radians is 2 pi thirds. Now solve for radius algebraically. Does everybody see what I'm doing?
Yeah.
So I'm going to do it like this. Multiply both sides by 3, because I am pretty good at algebra here. So we have 9 pi is equal to R times 2 pi, right? Divide by 2 pi. Pi divide out. 9 divided by 2.
7.
4.5, right? So 2 pi divided out. So our radius is equal to 4.5. Or 9/2. Does that make sense, everybody?
Yep.
Okay. Last thing. Look up here. I'm going to give you the rest of the time after this last example. So it says solve for x. So looking at this, could we solve for x?
Possible.
So set up a true statement, solve for x. If this is x, isn't this a central angle?
Yes.
So isn't that equal to x?
Yep.
If this is 6x plus 4, isn't this 6x plus 4?
Yep.
Now I could either solve this way saying those two things, 2x plus 6x plus 4 equals 180. That's a true statement, right?
Yes.
Or I could say all those angles, x plus 2x plus 3x plus 2x plus 6x plus 4 equals what? All the angles out of be what? 360, guys. This is a secondary 2-level problem. We've set up a true statement and solve for x.
38.
Finish the worksheet. Go.
Can't do that.